Hey everyone, Mr. Skelton here. We're back at it with lesson 6 in unit 1, and today we're going to be talking about composite functions. Composite functions. This is a lesson that sometimes can cause some confusion, but again, a lot of this is just recognizing the notation and being able to interpret what that notation means. So let's jump right into it here. Obviously the main goal for us today is to be able to perform a composite function. Well, what is a composite function? Basically, a composite function is this. It's one function inside of another. And I'll show you how that works here. Okay? So I got kind of a real-world application to it, try to make sense of actually what a composite function is and how, again, you can apply it. So some of you may or may not shop at Kohl's. I know shopped at Kohl's a time or two, but they usually have a lot of coupons, right? They have Kohl's Cash, and then sometimes they have like save 30, save 20, save 15%. They got a lot of deals always going on at Kohl's. So I'm going to kind of talk about a situation here. There's two situations that are taking place here when you go to Kohl's. The first thing I want you to understand is you have a coupon, and you have a coupon for 30% off. That's the coupon. You also have a coupon that is just a $10 discount. All right, so you can save $10 off of one item. Now, usually at Kohl's or at any other place, you can only use one coupon at a time, and you can't apply more than one coupon per visit. But we're just stay with me here. Let's just imagine that you can use both. So the million-dollar question becomes this: do you save more money if you take 30% off of the item and then subtract $10, or take $10 off and then take 30%? Now, some of you may be able to answer that question right now in your head. You can kind of do the math or think about the math that's involved in those two scenarios. But let's take a closer look at it so that I can kind of better explain to you how we can set up a composite function here and actually prove which one is cheaper. So we're dealing with a $100 item. Okay, so we're talking about something that costs $100. Let's just write a basic function for 30% off. If something is 30% off, what are you actually spending on the item? You're actually paying 70% of whatever the item is, right? If it's 30% off, then you know it would be 70%. So for example, you take 100 and 100 times it by 0.7. Obviously you know this, but it's 70. So you get $70. Okay. Oops. So 70% off, or excuse me, 30% off, which means 70% of the item, which is $70. If you take a $10 discount coupon and we want to write a function, notice I have the first function is f of x. So this is the first function. F of x is 0.7 or 0.70 times x, whatever x is. X in this case was 100. For the second function, when we're talking about the $10 off, we would simply just write whatever the dollar amount is, subtracting $10 from that total. That would be our g of x function. So really we have two functions. I'm going to write them off to the side here. F of x equals 0.7x, and our second function is g of x equals x minus 10. All right? Now, the sale first. So I'm going to go through the sale first, meaning if we took 30% off and then did the discount, what would that be? Well, if we did the sale, right, we would take our $70 and we would take $10 off of that. So 30% off would give us $70, and we would basically do this, 0.7x, and then subtract the $10. So if our item is $100, 0.7 times 100 would give us 70. 70 minus 10 would be 60. So if we applied the 70 or the 30% off and then applied the $10 off second, I'd be paying $60 for that item. So let's go ahead and apply the coupon first. We're going to take our x minus 10, okay, and then we are going to times that by the 0.70. So if I take my $100 item, I would have 100 minus 10, which is 90, and then I would take that 90 and times it by my 0.7. So if you take your calculator out and go 90 and times it by 0.7, you would have $63. Sorry there about the power surge. You'd have $63. So we were able to prove here real quick that obviously if this was a situation that could occur at Kohl's where we could apply 2 coupons to one item, we would definitely want to take the 30% off first and then subtract the $10 second. We would save $3, okay? That is an example of a composite function when you're basically inserting one function into another. Now, the hardest part about composite functions is basically just understanding what you're looking at. So, kind of like what we did in the last unit here, this, and I'll tell you how to read that, and this are the same exact thing. It's just written differently. So these are the same. This would be read out loud as g of f of x. That's how you would read that out loud. G of f of x. This means that you're taking the f of x function, which in this case is 0.7x, and you're plugging it into the g of x function, which would be the x minus 10. Okay? The other way to when you see this on your paper, another way to write this is this. And this remains the same thing. You would read this out loud, g of f of x. Okay? And here's where I don't want you to get confused, and I see this happen a lot with students. The last lesson we did, we had one where we had g times f, and then we had an x. My point being this: you have to be very careful when you do these to work slowly. Make sure you know the difference between a times sign, where you would just be timesing these two functions together, versus the O, right? The O, kind of like the open circle, that means composite. So just be careful with that when you start to work on these. All right? So over here, this would mean, this was our f, you would read this as f of g of x, so you're taking the g of x function and you're plugging it into the f of x function, or fog, or f of g of x. All right? Let's turn it over on the back and work some of these problems so that I can kind of give you some examples that hopefully makes a little bit more sense to you. Okay. I know this was a PowerPoint, so the answers are already given to you, which is okay at the end of the day. Here are the two functions that we're going to be working with. We're going to be working with f of x, x squared plus 2, and g of x being 5x. Okay. So, me personally, whenever I see this notation, I always rewrite it as this. This just looks nicer to me, and for me, it's easier to apply. And what I mean by that is this. This means f of g of x. Now, normally, if I put my finger here, my finger's probably a little too big. If I cover this up, right? If I cover that up, what's normally there? There's usually an x there, right? F of x. So just pretend the f of x, we're talking about the f of x function, which is right here, x squared plus 2. Well, if there was the number 3 there, so let's just say for kicks and giggles that, I'm going to write it off to the side, that I said, hey class, what's f of 3? What's f of 3? Well, here's your f of x function. Normally there's an x there, but now there's a 3. So I want to know what this function is, and highlighted. I want to know what that function is when x is 3. So you would take this 3, and wherever you saw an x, you would plug 3 in for. 3 squared is 9, right? 9 plus 2 is 11. So you would say, hey, that's 11. Well, when you do composite functions, this would always work for me. I would cover this up, and I would say, okay, this is usually f of x. Well, what's in place of an x? I'm not substituting numbers now in for x. I'm going to substitute in the g of x function wherever I see an x. So just like on this problem here, where there was a 3, you substituted a 3 in for x. Now instead of a 3, there's the g of x function, so you're going to take this entire function, which is f of x, or which is g of x, and you're going to plug it in wherever you see an x into the f of x function. So it would look like this. F of g of x would equal, instead of x squared, you're going to plug in the 5x into the x function, so it would be 5x squared plus 2. And you would simplify that. 5x squared would be 25x squared plus 2. That's a very basic, a little sideways, that's a very basic composite function. Okay. Now number 2 says g of f of x, and again I would rewrite that as g of f of x. And again, I'm going to use that same logic. right? I'm going to cover up the f of x. Normally, there's a number there, or it's just g of x. So I'm going to do another quick example. I'm going to say g of 4, okay? Okay, class, g of 4. Well, normally there's an x here, but now there's a 4. What does that mean? I want you to stick a 4 into the g of x function wherever you see an x. It's just pure substitution. Normally there's an x, so instead of x, you plug in a 4. Well, what's 5 times 4? 20. Very good. So, when it's composite functions, when I remove my pen, instead of a 4 being underneath my pen and substituting the 4 in for x, what are you going to substitute in for x? The f of x function. So it would be written like this. 5, now instead of x, you're substituting in what? X squared plus 2, because that is the f of x function. And now you would distribute and get 5x squared plus 10, which you can see here and here. Okay? Now, another quick example of how you can apply this is sometimes we can give you a composite function, and instead of writing x, it's just a kind of a continuation of the problem here. I can say, okay, f of g of x when x is 5. So you actually do the f of x composition, which is right here. We already did that. And now I'm just saying, okay, now plug in a 5 for x. So you would just go 25. You plug in the 5 for the x there. You'd square it plus 2. So you take your calculator out. Well, you really don't need it. 25, right, times 25 is 625. Add that to 2, and you get 627. Okay? Likewise over here, we already did the composition of g of f. We completed that right here. Remember, g of f of x was right here. And so now we're just going to plug a 5 in for that x. So it's 5 and then 5 squared plus 10. So again, I'd have 5 times 25 plus 10. So you get 125 plus 10, and you get 135. Okay? Let's do another quick example here. I'm just going to make something up and just have you try, just so you can have one more example of this. So I'm going to say a of x is equal to 3x, and I'm going to say b of x is x squared minus 1. Okay? So those are your two functions. Okay? And let's do this. I want you to do a o b of x. Okay? Put that in parentheses. So I want you to try that. Go ahead and hit pause and try it. See what you come up with. Okay. Me, if I was doing this problem, the first thing I would do is rewrite this. For my money, I'm going to write it as a of b of x. So again, what is this truly saying? This is saying I want you to take the a of x function, which is listed right here as 3x, and normally there's an x under here, a of x, but instead of plugging in an x, or where there's an x, I want you to plug in the b of x function wherever you see an x in the a of x function. So what does that mean? I'm going to go 3, and then because there's an x here, I'm going to substitute in for x the b of x function, which is x squared minus 1. And we would just simplify that. 3x squared minus 1. That is a of b of x. Okay? Let's try it the other way. Let's see if we can do, I'll just write it as b of a of x. Okay? So again, what is b of a of x? This is a composite function. So normally there's just a giant x there. So we're talking about the b of x function. But now instead of like the number 5 there, or the number 7, and you plug 7 in here or 5 in here, what are we plugging in for x? We're going to plug in the a of x function into the b of x function wherever there's an x. So this would be, instead of x, we're going to write 3x. We're going to square it, and then we're going to still subtract 1. That becomes 9x squared minus 1, and that is b of a of x. Okay? So I know I gave you another example there, but I just kind of wanted to show you something else besides just the one example. As always, if that's still not fully making sense to you, by all means, let's talk about it when we come into class. I can show you some more examples on the board. We can have some good discussion, and I look forward to seeing you, okay? Take care.